to where we're at in the lecture. It's been a long time, it feels like, right? At least for me, it feels like a long time. It was a long weekend. What were we talking about? Equilibriums and ice tables and how to determine, based on concentrations, what equilibrium concentrations are or initial concentrations relative to equilibrium constants, right? And then we also looked at another way to view equilibrium constants as Kp, or pressure constants, right? So there, if we have gases, we can look at the partial pressures in the same way we look at concentrations. Right? But there we need to have some gas knowledge, which we demonstrated with the partial pressure divided by total pressure equaled the mole fraction, if you recall, right? And that's how we determined the Kp in that situation, okay? So we use the ice tables for concentrations, and then we use different creative ways to determine the Kp based on partial pressures and gas laws. Okay, with that being said, now we understand what Kp, we understand what Kc is, right? So what if you have concentrations of some stuff in a chemical reaction that are not at equilibrium, right? We can use ice charts, but what are we going to find with that? So in the concept of an ice chart, let me just make sure this is clear when we talk about ice. ICE, what does the I stand for? Initial. What is the C? Change. And what is the E? Equilibrium. Equilibrium. So then, that's interesting, because then, if this is equilibrium, right? Then, if we're not at equilibrium, how does that factor in? Right? Think about that, right? These are things to think about. It's not always as straightforward. So we're going to predict change if we know what the Kc is, which is always helpful, right? So let's just say we know the Kc, not necessarily through ice, say it was given. And then I have some level of concentrations, don't know what they are. And I figure out what the constant at those random concentrations are. If they match Kc, then I'm at Kc, no big deal. What if they're less than Kc, or what if they're more than Kc? Okay, that's what we're looking at. And we'll call that the quotient constant, and we'll call it Qc. And we'll see how Qc relates to Kc based on what the number is. If you know Kc, then you can estimate where Qc is and the direction of the reaction, right? Because we're in an equilibrium, so is it going forward or is it going backwards? Based on this number relative to this number. And of course, if they're equal, then they're at the equilibrium already. That should be pretty straightforward. Okay. Lots of words here. There's the Qc that I mentioned. So this is the formality of looking at the quotient constant, Qc. And if I look at something like this, for example, so here's that classic generic equation at equilibrium. And here's the Qc, just like Kc. Okay. I could also do Qp. Okay, it doesn't matter which one. And I now say, okay, if my Qc is 0, I'm clearly going to move from the reactants towards the equilibrium in this direction. If my Qc is really, really high, let's call it infinity, then I'm way over favoring the products. And it's likely it's nowhere near my Kc, so then the reaction would be favoring going backwards to stabilize into that dynamic equilibrium. Okay? So if I'm anywhere along here, less than Kc, I'm going to be moving in the forward direction based on the balanced chemical equation. And if I'm somewhere past Kc, then I'm going to be moving backwards towards that equilibrium at Kc. If I'm at Kc, then Qc equals Kc, and I already know my equilibrium. Okay. So we're going to obviously apply this. Okay, so we have a plot here. Okay, so A is going to B, B is going back to A. They're both gases, and my equilibrium constant is 1.45. So if I figure out I have certain concentrations, it gives me a Q of 0.55, that's less than the 1.45, that means that in this equilibrium, A is favoring going towards B in order to stabilize itself into the proper equilibrium at that temperature and under those conditions. If Q is larger than K, that means that I have more of this than necessary for the equilibrium. It's now going backwards. Okay? And if they're equal, I'm at equilibrium. There's not going to be any change in concentration from either side at that moment. Doesn't mean that they're not in a dynamic equilibrium where they're still moving forward and backwards. They're just doing that at the same rate, right? So here's a little table or chart that just sort of emphasizes, if I look here, I have my concentration, these are my reactants going towards my products, and over here I have my Q or K. So at this line here, I'm saying this is K, right? So that means that everywhere up to that K and everywhere past that K are all my Qs. Okay. So if my Q is less than K, then the reaction is still moving towards the product. If my Q is more than K, then it's coming back down and moving right to left from product to reactants, and that's what this is demonstrating. So here you have Q is less than K. Down here, this is my QK, so Q is less than K. So therefore, I'm going to be moving towards the right of this graph and moving from reactants towards products until I get to K. Here, if Q is equal to K, I'm right at my equilibrium. And up here, my Q is greater than K, so it's going to be moving down or to the left, or to the left of the reaction, creating more reactants as opposed to products until it gets to the equilibrium. That's all that's saying. Looks like a complicated graph, it's not. It's pretty straightforward. Just those 3 points, the same things we're talking about. Okay, so this is all the same thing. So QC equals KC, reactions at equilibrium. QC is less than KC, reactions moving towards the right. QC is greater than KC, reactions moving to the reactions moving to the left. Okay. Multiple ways of saying the same thing. Okay, so let's try. So what I have here is I have this reaction and I have these concentrations. I'm also given that at 900 degrees Celsius, Kc is equal to 3.59. So what am I supposed to do here? Plug it in, solve for QC, and see how it compares to Kc. Right? Okay, so if we plug in these numbers here, it's already given. So is the reaction mixture at equilibrium? That's the first question. We can figure that out real quickly. And if it's not, which direction will the reaction proceed? Usually that implies that it's not at equilibrium. So let's go ahead and look real quick. What is our QC equal to? And we get 1.02. Okay. So 1.02, what was the Kc? 3 point something. So then what's happening here? Is it moving to the left or the right, or is it at equilibrium? It's moving to the right. It's QC is less than Kc, so it's going to move to the right towards more product and less reactant. Okay, no big deal.
We can take the exam now.
And that just tells us QC is less than Kc, and therefore reaction proceeds to the right, or towards the products as we're defining them and away from the reactants. Is that okay?
Yep.
Yes.
Okay. So, you guys already know this. Up to now, we've tried to figure out what the Kc is, basically, right? Mm-hmm. Using the equilibrium constant setup. Mm-hmm. Now they're just saying if you have QC, if you have Kc, mm-hmm. then you could figure out what some of the concentrations are. That's it. No big deal.
Okay.
You guys already know that, though. I think we've not only talked about it, but that should be blatantly obvious, right? If you have some unknowns and you're given certain unknowns and you have one left, then you solve for the one that's left.
Right.
Right? It doesn't matter which side of the equation or what the unknowns you have or don't have are. You could always solve for the other ones.
Some concentration.
They give, yeah. So here they're going to give you, let's see. So let's see. They have to give you some if there's more than one. Right? How could there possibly be not more than one? Is there situations for that? What is the thing we have to look at? Let's go back when we're looking at equilibrium constants. We're talking about equilibrium. What's the very first thing we need to have? We need to have an equation, right? Have to have an equation. Within the equation, what matters towards the equilibrium constant? Gases and things in aqueous solution, right? Because the other things don't change, they're basically part of the constant. So let's make sure that we're back in, so that means that different things can apply there. Pressure will matter for gases, right? Volumes if it happened to change, but of course that's, only if you have a movable piston or something like that. What else would matter? Concentrations and partial pressures. And that's how we solve for the equilibrium constants. So that means if I have a solid or a liquid, they're not included in these changes. So let's make sure that we remember those things. Right, so I look here, first thing I say is there's my equation. Second thing is gas, gas, gas. I'm okay here. That's important. Okay, I want to bring you back to make sure that when you're evaluating these, you're looking at them from the proper perspective. Okay? So then it says Kc for this reaction is equal to 0.0025 at this particular temperature. If an equilibrium mixture at this temperature contains this number of moles of nitrogen and this number of moles of oxygen per liter, what is the equilibrium concentration of the third thing up there, which happened to be the product in this case? Because I could give you a reactant, it doesn't really matter. So what's the first thing I need to do is what is Kc? Kc is equal to NO concentration squared over N2 times O2, right? We know what these are. This is per liter, this is molarity, so this over this is just 0.031 mole, right, molar. This is 0.023 molar.
Right.
And I know what the equilibrium constant is, so can I solve then for the concentration of NO?
Yes.
Of course, that's it. That's all this section is.
So you just
Like I said, this
multiply.
is stuff you already know, right? From just doing all the things we've done up to now.
Right.
So we can go ahead and apply this. Here's my this is what I'm looking for. I put it all into the reaction here.
In second order?
And I get this equals this. Because I'm solving for this, I plug in these three things. No big deal. Multiply those out in my calculator. Then I do what? Square
Second
root
order.
both.
Right.
So I square
Second
root it,
order.
and I end up with 1.3 times 10 to the minus 3
Squared.
molar of NO. That's my concentration of NO. Nothing really unique or fantastic here, right? This is all stuff based off what you know.
To cancel it.
So that's squared. The only way to get it out is to square root. Okay, let's try another one. So this is the synthesis of ammonia. And at equilibrium, I'm now looking at Kp. So my Kp value is this at that temperature. In this mixture, the three gases, partial pressure of H2 is given. The partial pressure of N2 is given. What is the partial pressure of the ammonia? This is the same question,
thing.
right?
Yeah.
Yeah, just pressure. Same exact thing. Okay. So I put this in context, make sure that I have my square and my cube here. I know I'm solving for this, so I move these two things over. Right, so now it's this equals this. I plug in these, make sure that's cubed. That's one place you get stuck on an exam making a mistake because you're moving quickly, is forgetting the 3 here. Right, that's a prime area where you can make an easy mistake of doing that. So that means I have this, it's cubed here, then times this is going to give me P, the partial pressure of ammonia squared, and then I take the square root of that, and I get 2.24 times 10 to the minus 3 ATM. That's the partial pressure of the ammonia in the system. Okay. Very similar to the other one. Doesn't, by the way, this doesn't always have to be squared. If this is not squared, this is easy. I don't have to square root it.
Yeah.
If this is cubed, I take the cube root, etc. Okay. It just so happens that both examples are squared for some reason.
This goes back to what you're talking about the direction and change. Is it possible for you to have like a QP when you're talking about partial pressures versus a QC for concentration?
Yes.
Because there's a problem in here.
Yes, but it would be, this wouldn't be, you couldn't plug these in with KP. You'd have to plug it in with QC or QP, just to keep that in context. This is specifically, when you see the K there, you're at equilibrium. If it's Q, then you're not, right? So you gotta make sure, because these were given as partial pressures at equilibrium. And this is given as KP. So, but you can have a different situation where you're looking for QP and then comparing it, but then you have to make sure your concentrations are, you know, in that sense.
Still working on it?
Yeah.
Okay, moving along, we have plenty of time. We're now going to expand our knowledge of ice and how to use it. So, we can now figure out what some of our equilibrium constants are with some part of it not being known. In other words, when up to this point when we've used ice, we had an initial concentration, we had an equilibrium concentration, and then we just took out the difference to figure out the change, right? And then that change was based on the balanced chemical equation, the molar ratio, as we went across for the change, and then we were able to solve for the other, whether I'm looking at equilibrium to initial or initial to equilibrium. Everybody okay with that? That was how we did the ice.
Yeah.
What if we don't know what the actual change is?
Algebra of the number minus.
Then we could use a variable, right? Then we could just call it x.
Right.
Minus x, plus 2x, minus 2x, whatever. It's always going to be minus in the change if I'm in reactants, and it's always going to be positive in
Product.
the product if it's the change.
Right.
Assuming I'm starting with initial and going to equilibrium, right? But as we just saw, if I started with something elevated in terms of my QC concentrations, then it could be going the other direction, right? We're not going to talk about that, but just wanted to make sure that you're aware of that. Okay. So all we're going to do now is use a variable in order to solve for the change and therefore the concentrations. So that's the only spin on what you already know here. So here's my A going to 2B. I look at it, I see that I have my gas and my gas. And what I'm showing you here in my ice chart is that I have a concentration of 1 of A, and so if I'm starting initial, I have this initial, and that automatically means my product is at 0. I know that I'm going to lose something here, so I don't know how much. So I'll just say I'm losing minus x, that's my variable. If I'm losing minus x, I'm gaining 2x because it's a 2-to-1 ratio. So here's my 2x. So now when I put this together, I say 1 minus x and plus 2x. That makes sense so far?
Yeah.
I just don't have numbers this time.
Yeah.
Before I gave you numbers, it made it easier. Now you're just using variable. But I could now put this into my what?
Constant.
My constant. And if I know the constant, which is why we did that little demonstration just before this, if I know the Kc, then I could solve for x using basic, simple
And then you have to
mathematical
remember
calculations.
To put it back in and solve for that.
We're going to put it back in, and then we're going to solve for x. That's all we're going to do. That make sense?
Yes.
Which is why the last set, when we looked at the equilibrium constant, you know it, then you could, as you know it, then you could solve for the concentrations at equilibrium if you know one or the other. Now you know one or the other in terms of a variable, and then you solve for the variable to determine the concentration at equilibrium of whatever reactant or product you're looking for. Okay, so let's go ahead and try that.
We are doing
Whoops.
example.
So I have the synthesis of nitric monoxide, and it says for the reaction shown below, my initial concentration of nitrogen is 0.2 molar. My initial concentration of oxygen is 0.2 molar. Find the equilibrium concentration of the reactants and products in this reaction. What else must I know here? I need to know Kc. If I know Kc, then I could set up an ice chart, figure out what my equilibrium concentrations are, put those in the equation for Kc with Kc, and then solve for the variable. Once I know the variable, I could then go back and figure out what the concentrations are of these at equilibrium. So the only difference here from what you've learned before is that I don't have a concentration at equilibrium yet. Before I gave you a concentration, one of these at equilibrium, that allowed you to figure out the change and the exact amounts of everything. In this case, you don't have any concentration at equilibrium. So then I set this up. Here's my ice chart, ICE here. This at the initial is 0.2, 0.2, what is this? 0. What's the change here? It's going to be minus x, minus x, plus 2x. So then this is going to be plus 2x in terms of my equilibrium concentration. This is going to be 0.2 minus x. This is going to be 0.2 minus x. And if I have Kc, I could put all that together and solve for x. Once I solve for x, then I say 0.2 minus whatever my x is my concentration of N2. 0.2 minus x, whatever that is my concentration of O2. And 2 times that x is my equilibrium concentration of the NO. What's that? Does that make sense?
Yeah.
Okay, so let's take a look. There's my Kc that has to be given here in order to solve for this. And now, you notice how I love setting this up here. The N matches this column, the O2 matches this column, the NO matches that column.
Right.
Really, really important. What if I had a solid in there? I could match it to a column and it's just going to be a line through it because it doesn't do anything. There's no change.
Right.
Or at least, presumably, there's no major change. Not enough to matter.
But you have to include it?
It's good to include just so you can see it, but no, you don't necessarily have to include it. But you want to make sure that, I like these to be on top over the equation. I like the equation over it so I know this is really important. Now this is going to be important more so later than now when we get more complicated ice charts. But having this equation over this allows you to see what it is you're working with. Because we're going to get into where we have multiple different ice charts for 1 or 2 different reactions, and you got to make sure you know which reaction you're dealing with in each case in order to solve for what it is they're asking.
So, and just to say hypothetically, if one of the reactants had a coefficient, we would scroll down and that would be like a minus 2x?
Could be. If this was a 2 here,
Yeah.
then this would go as minus x. That'd be minus 2x. If this was a 3, minus 3x, whatever it is, absolutely.
Okay.
The same way this is plus 2x here. Because of the 2 of the coefficient, that's the molar ratio within the balanced chemical equation that you're comparing the number of moles going across this way.
Because I didn't know if that 2 came from adding those 2?
Nope, this 2 came from that 2.
Okay.
Literally, this is 1, 1, 1, 1.
Okay.
This is
It's just the
added.
molar ratio of the balanced chemical
This
equation.
is the molar
That's the
ratio.
difference in the change from one to another when you're talking about the same amount.
If it would have been 0, we just put 1.
So here, 0.2, minus x, plus 2x.
Because this is
This
x.
0 to plus 2x gives me 2x.
You don't have to put
0.2 minus x gives me 0.2 minus x. 0.2 minus x gives me 0.2 minus x. Once again, I don't know the concentrations there. I just simply plugged in a variable in order to solve for it. But I know Kc, so I could put all of these things in the Kc equation and then solve for x. Once I solve for x, so then I need to replug the x in order to determine what these concentrations actually are. Okay. So here's my Kc, which was given. I write this up properly here. I get the 2x squared, and I get 0.2 minus x times 0.2 minus x, which is the same thing as 0.2 minus x squared. So
Right.
keep that.
Yeah.
Okay. So that doesn't become confusing. And that's equal to whatever was given, which was 0.10. So of course I moved this up here, and then I start to multiply through. Okay, in this case, since these are so, okay, you're going to do different things. This may not be squared and squared, and then you'd move it over here. Since it is squared here, I could just take the square root of both. That takes the squares out of there, right?
Right.
And then this has to be squared. Depends on whatever you have per side. You may not have that. So if I take the square root, that square goes, this becomes the square root of 0.10, which is 0.316. This underline indicates that they're only supposed to be 2 sig figs, but I'm going to carry over the numbers through the calculation until the end. But I'm going to make sure that I know that I only have 2 sig figs here. I move this up here, or maybe I move this up and then flip it, and I end up with 2x equals this times this, which is what I get here, and this times the minus x, which is what I get there. Just simple basic math calculation. Rearrange, I get this, so when I say rearrange, I'm simply taking I'm multiplying this through, then I can take this and I can add it to this side, and I have whatever I have left, which is here. Then I just simply take this, divide it by this, and my x equals 0.027 molar. So after you do all the calculations, play in your calculator, then that's the number you get. Am I done? No. What do I now have to do? I have to plug it in. So what was it, 0.2 minus 0.027? That's going to be my concentration of both reactants. And this squared is going to be my concentration of my product. Right?
Would it be times 2, not squared?
Where do you get the point?
Two times this times that.
Square root of 10?
Yeah.
This times itself is squared root.
I thought it was 2x, not
Oh,
x
maybe.
squared.
Yeah, that's what I was
No, you're right.
wondering.
Yeah, you're right. It is just 2 times. Yeah, absolutely. So it's 2 times this. Yes, absolutely.
Right.
Okay, so there's your O2, but this just shows that the concentration of O2 equals the concentration of N2, and so I could just do it once to solve, and the 0.173 molar is equal to the concentration of the O2 and the concentration of N2, and then for NO it's 2 times that, which is just 0.054. And those are my concentrations of my reactants and products at equilibrium when you had no idea what they were. All we had was the Kc. We knew the equilibrium constant, and what else did we know? The initial concentrations. So we've just expanded how to solve for ice problems, right? Before, you were given some numbers, and then you just take the change of those. Now, you're not given equilibrium concentrations, just initial concentrations, and from that alone, you could then solve for the equilibrium concentrations. Okay, anybody have any questions? I'm making it look really easy, hopefully.
Yes.
Good. I'm sure we have another example here, yes. Okay, so now we have the decomposition of ammonium hydrogen sulfide to ammonia and sulfuric acid, or hydrosulfuric acid. See, at 25 degrees, the equilibrium has been reached. So what is the pressure here? So this is interesting, okay. What's the first thing you should notice in this equation? The solid. The solid, right? So that is not going to factor into anything we do here. That's going to be assumed to be part of what? Our Kp. That's important. So this I'm not worried about. I'm only worried about these 2 things here because they're both gases. Okay. So my Kp at 25 degrees is 0.108. So my Kp is equal to this, because the solid doesn't count. That's part of my Kp. Everybody okay with that? That should be okay. Now, I want it. What am I going to have to do here? If my Kp equals this, is that pretty easy to solve for what each one is? Yeah, these are basically this times that. Partial pressures, it's a 1-to-1. Should be pretty easy, right?
Yeah.
I just plug in. So my partial pressure of ammonia is equal to my partial pressure of the hydrosulfuric acid, which is equal to X. So arbitrary, it could be Y, Z, whatever you guys want, right? X and X is the same thing as X squared, which is why these things equal just X themselves. And then I say X is equal to this. What is this here? Maybe I should write this out. I sense some silence. Let me make sure that everybody's following along. All I did was I said Kp is equal to partial pressure of NH3 times the partial pressure of hydrosulfuric acid, which is equal to 0.108. Okay. Where did I get this from? I got that from this equation, which is why I need to know this. This 1, which is why these are not, they don't have any exponents on them. Okay, otherwise I'd have exponents. So then I say, well, this is X and X, 1 and 1s, right? So Kp is equal to X times X equals 0.108. So that's the same thing as X squared equals 0.108. And if I take the square root of both sides, X is now equal to 0.329. That's all. I didn't necessarily need to convert these to X, I could have left that there. And just said this times this, because it's a 1-to-1 ratio. Go ahead.
How would you know that they're equal to each other and not like 0.6 and
1-to-1 ratio.
Oh, they're 1 to 1 ratio.
Going back once again to the molar ratio of the balanced chemical equation, which is why you must know that.
And if the ratios weren't equal,
Then this would be X squared, and then you're now taking X to the third, take the cube root, and then you solve for X, and then you X squared. So this is just the square root of 108. 0.108 gives you 0.39. So the P total is what?
That plus.
This.
Plus that, the section.
Absolutely. That's my total pressure. And what did it ask us to find here? The total pressure. If it just asks for the pressure of one of these, then that's the partial pressure. It would just be 0.329 of either in this case, because both of them have a coefficient of 1. So it's a similar trick that we just used to the concentrations, where we use the ice chart, and here we're just simply saying the same kind of thing. We're just assigning it as X. This is a little easier in this case because just plugging it in and solving it for you. Okay. Try another one. So what's going on here? What do I need to do? The first thing is you see concentration, you can do what? Ice charts. Do an ice chart. Okay. I have concentration at equilibrium. That's interesting. So if the concentration of CO at equilibrium were found to be 0.010 molar, what would be the equilibrium concentration of the H2? This is kind of easy, right? This is easier than the ones we've already done. I have my Kc. Does this factor into the, no, that's already embedded in there.
Right.
So it's just going to be 1 over the concentration of H2 squared times the concentration of CO, right? I'm giving you the concentration of CO, so you're solving for the concentration of H2. Okay, so I really don't need to do anything other than just plug in. I don't need to make an ice chart here. Okay. This, everybody's okay with this, of course?
Yeah.
All I did was move this up, move that down. That came up. This went down as I crossed sides. I know the Kc, I know the CO concentration. I could plug those in, 1 over that. And I could just take the what? The square root of this and the square root of that.
Right.
And that gives me, so this is just 1 over this, gives me this, and then the square root of that and the square root of that gives me 2.72 molar. I didn't need to use an ice chart here. This was an easier problem. So what does that tell you? Don't jump to conclusions on what to use. See what's given, what you need to solve for, and then go ahead and solve. Because in the exam they'll be juxtaposed, right? Where one you might need to use an ice chart, another you may not need to use an ice chart for the concentrations.
Right.
And then use whatever type of thing you need to use for the partial pressures and solve for whatever they're asking for. Okay, so sometimes you may need a more elaborate setup and sometimes not.
Where did you get the 1 from? I'm sorry.
What do you mean?
The 1 over.
How do you set up the Kc here?
Product over
So what's the product?
the liquid.
Right.
Okay, so you just put it as 1.
Yeah,
Okay.
because if there's
Well,
anything
what
on top.
would you put it at? Just think about it for a minute. Can you
I
put
was
it at
just
0?
not gonna include it. And
didn't.
then- Yeah.
But it's still over something, right?
See, I didn't do that. I just multiplied it out and then put it
Show me what you did.
So I did it like this, 13.5 equals, and then I put.
13.5 equals.
I put CO and then plus, multiplied by H2 squared
Like this, am I doing what you said?
Yeah.
And then what?
H2 squared. That's what I started with.
But those are the
And
reactants
then-
they need to be on the bottom. Products going on.
So this is KC, right? That's what you're
Yeah.
trying to show here.
Yeah.
So this is products over reactants, right?
Mm-hmm.
Are these reactants or products?
Reactants.
So they go down here,
Yeah.
not up here. So if you're left with nothing here, that's just what?
1.
Is that okay?
Is the one supposed to be an inference of a equilibrium?
The one is simply a placeholder.
Okay.
So that, right, if I put 0, the whole thing's 0.
Yeah.
Or undefined, or whatever, right?
Okay.
It's just holding the place, so, I mean, if I put anything else, that changes what these are, right? If you have something times something, for example, if I say 25 over 50, let's just say, that's the same thing as saying 1 times 25 over 50.
Oh, I see.
Right, right, does that help? Then I take away the 25, it's still 1.
Yeah, yeah.
Okay, does that make it better?
Yeah.
Okay, so this one's okay. Okay, now, so when you're solving for x or that variable, the way we've shown it up to now, it all depends on what you're left with. So a lot of times, it's just as easy as we did it. Sometimes it's more complicated than that. And in those cases, you have something like something, say the variable squared, plus or minus something times that variable, plus or minus times the number, equals 0. And there, how do you solve for x? And if you take it back to, I think, what is this, algebra 2 or something, a long time since I took it. But you would solve it with the quadratic equation. And that's how you solve for x. The problem with solving with the quadratic equation is you end up with 2 different numbers for the variable. So then you just use your logic. One's going to be plus, one's minus. In that context, then it's always going to be the one that's plus, because you can't have a negative concentration. So let's take a look. Just to recall, here's the setup of the format of a quadratic equation. A is just a coefficient. That's a number. X squared is your variable. Plus or minus b, another number. X, the variable, plus some number or minus some number equals 0. And as a result of that, then you solve this by saying, using the quadratic equation, which is minus b plus or minus the square root of b squared minus 4ac over 2a. So b is just whatever this is here, this coefficient. A is whatever this coefficient is, and c is whatever that coefficient is. And you're going to get a plus and a minus number usually out of this. Okay, and that's how you solve. If you had this come out after you've done your ice chart or whatever else, this comes out, then you can't just straight solve for x, and this is how you would solve for it.
What if it was factorable? You can just factor it equal to 0.
What do you mean by that?
So if you were able to factor it,
So give me an example here.
x squared plus 2x plus 4.
Okay.
So x plus 2.
You want to do this?
Yeah.
Yeah, you can do that.
Okay.
But the numbers they won't be that clear, right? They're not gonna be
Let's see.
clear like that.
Okay.
What do you got? Plus.
Plus 2.
No.
No,
plus
that was
minus.
minus.
Oh, that was
Wait, no,
Oh,
that
that's
would be
not-
negative.
That's
No,
not
you have to-
factorable.
Should it be
plus 4.
negative sign?
Yeah. In order to factor it, easily one of those. needs to
This
be
has to be negative, or?
If that one's negative, then it will.
If you had one that, I think the only point is that's not a good, that's just not a good example, but I see what you're saying now. If you had one where you could do this, then you set them both equal to 0, and then you get your 2 x's. Right.
Factoring?
Guess we need to have a math lab to come up here and explain this. But yeah, I see what you're saying now, yeah, that should be okay. But usually, it's gonna be hard to find that a lot of cases, yeah. Because you're gonna end up with things like decimals. And that's where that becomes much more challenging. So usually concentrations are not gonna be set in those nice numbers to do that.
Right.
Okay, so let's look at the decomposition of PCl5, gas, 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 so all these things are relevant. Initial concentration of this is given here. What is the equilibrium composition of the mixture here? And I'm giving you the Kc. Okay, so what do I do? ice, right? This time I'm gonna need ice, so I have 1, 0, 0, minus x plus x plus x because of the 1 for 1 for 1 ratio. This becomes 1 minus x, this becomes x and x. I put that into the equation, I get x times x over 1 minus x, or x squared over 1 minus x equals whatever the KC was given at. Up to this point, we're okay?
Yeah.
Okay, nothing special here. Okay, so then now I'm solving for x here, so I'm just moving this up here, and then I'm multiplying this through both positions. I get 0.0211 times 1 minus x gives me x squared. And of course, since we're working on quadratic equation, that's what's gonna come out here. X squared, I'm gonna move this over, plus 0.0211x minus 0.0211 equals 0. All I did was move this over and move this over. And you can see here, a little harder to factor, right? Get the decimals and stuff. But now I just use the quadratic equation. Okay. So what was that? Minus b plus or minus the square root of b squared minus 4ac over 2a, right? Okay. So then that's the only way I could solve for x here.
Right.
Why do I care about solving for x again? What's the bigger picture?
Because then you know what you're
I'm looking for the concentrations at equilibrium.
Yeah.
I just meant to put it in perspective. It's easy to get caught up in the minor details of solving something and then lose track of why you're doing that. Because once you solve for the x, then you don't stop there. You gotta now figure out, unless x is the answer. Sometimes it's 2x, sometimes it's something else, something minus x, right? In this case, it's 0.1 minus x, or 1 minus x here. Okay, so I plug this into the quadratic equation. It's gonna pump out a couple different numbers because of the plus minus here. I'm gonna get this plus all of this, and then this minus all of that. So that's this here. That gives me two answers. Oops. Answer 1 is where this is plus. Answer 2 is where this is minus. So I get 0.1351 and minus 0.1562.
And you always get a negative number for one of them, right?
Usually. Right? It is possible to get a positive number there.
Yeah.
And if you did, then you wouldn't know which one was right or wrong. But of course, I'll make sure I don't give you one. You see what she's saying, everybody. In this case, it's going to be nice. Ideally, you get a plus and a minus. And why does that matter? So let's go back. Let's make sure we understand what the value, why that's even brought up.
Concentration times negative.
If the x was negative, would this one make any sense?
No.
No.
Okay.
Right? Let me rephrase this because I want to make sure there are a couple different things to think about here. This says initial. And the initial is you start with this and none of this.
Yes.
Under that condition, I can't gain more of this arbitrarily.
Yeah.
Right?
Yeah.
So if the x came out a negative, then this would end up a positive and I'd gain something. That doesn't make any sense.
Yeah. And you can't.
And I would lose something that I never started with.
Yeah.
Okay? Putting it in big picture perspective. However, what if they both came out positive? Now, how do I know which one is going to match in here? And that's what the question was. And that's what the answer was. I won't give you one that comes out that way. I will give you one on the exam, by the way. So this is something you will need to have to solve for on the first exam, just so you know. Right?
But you don't give it
That
this
should be
when it
obvious.
comes out positive and negative.
Yes.
Sometimes.
Is there any other way you could figure out which one was right or which one was wrong?
Solving for it and then seeing which one makes sense.
What's that?
Substituting both.
So in this, I could solve for the equilibrium, right? That's what I'm doing, the equilibrium concentrations. What if I knew the KC?
Yeah, then you would see which one gives
Then I
you the
match it,
right
absolutely.
KC.
Then I just match it, right? Right? Does that help?
Yeah.
But if I didn't know the KC, then obviously I don't know which one is the proper equilibrium.
I see.
That make sense?
Yep.
Okay, so that's why this is a good question. That's why I take you back to the beginning. Why do I constantly go back? That's the one thing people always make a mistake on. They get so caught up in whatever it is they're doing that they forget about why they're doing it. And they never go back and try to put it in place properly to figure out whether it makes sense or not. Where a lot of times it logically makes sense if you take that step back. right? And people at every level, not just at this level in academia, but through any job that you see this happen all of the time. People never want to take a look at back and big picture. They get so caught up that they can't get off of that. Keep going down, 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 and then they get to here, and then all of a sudden it's like, okay, what do I have? Right? If you stop along the way and say, what am I trying to do? Why am I doing this? What's the context of it? Because you could be doing something in the same thing for 2 or 3 or 4 different reasons. So then your reason to look back may be different than 2 or 3 other people at what you're doing. Because what you're doing makes more sense this way, what they're doing makes more sense that way. We saw these kinds of things in Chem 101, I think, where we looked at everybody remember when we looked at the difference in electron negativity? And we saw different charts, and we said, why are there different charts? Right? Depends on what you're looking at, depends on what matters more to you, right? So always keep it in context of what you're doing and what you're solving for and why you're doing that. And if you take that step back, you'll see very clearly a lot of times what it is you're trying to do and why. And it has to be in that proper context.
Could you go back to the previous slide? So if we knew KC would just equal all 3. It would equal 2x over 1.00 times 9 seconds.
KC would equal this times this over that.
Okay.
This. Which is what we do here, right? But if I already knew the concentrations, then I could solve for and I knew the KC, then I'd know which one came out appropriately. Okay. So 2 mathematical solutions exist, only one solution makes physical sense, that's the positive one, not the negative one, for what we just talked about. So now I gotta go back and solve for it. So 1.0 minus this is gonna be 0.86, that's my molarity of PCl5 at equilibrium. And then PCl3 is equal to Cl2, which is just X, and that is just simply 0.1351.
Okay.
And those are my concentrations, which is what the actual question asks for. Okay. Only thing I want to point out at this stage is that make sure you can do these on your own at home, and that you're doing them maybe think about it when you're doing it, that they're out of order, right? So on the exam, these are going to be juxtaposed. When you do one, could be harder than when you do an easier one, and et cetera. So make sure that it's not set in this nice sequence that I'm presenting it, and I'm not there explaining which parts to think about. You have to be able to look at them, evaluate what's needed to solve, and then do the solving. Okay? And they're not going to come in some perfect order that's set up the way these lectures are.
The book gives you in order, or
The book also is going to follow just like this. This follows the book essentially, right?
Okay.
Yeah. It's all broken down into these nice sections. You know, and on the exam, ideally, it'd be like, okay, you're in this section, a little neon thing flashes and it tells you the section you're in, because then you could assess it, right? But it doesn't do that. You're just going to go through and it's not going to be in the same sequence. They're juxtaposed. They're randomly matched to some sequence for your multiple choice, and then the other ones are given based on, you know, whatever we thought was more appropriate to have you solve for in a solving type of problem.
Yeah.
So keep that in mind. That's the tricky part of that. Sometimes you're like, okay, that's easy. If I follow this, I know what I'm doing. But then when you see them all over the place, then it's like taking it out of place, right? You ever see somebody you see once in a while on campus and you see them at home at a store, and you're like, I know who that is, but I don't know who that is. It's out of context, right? And that's how these problems are on the exam. So make sure that you're comfortable looking at things out of context, right? Where they're not in that nice format where you see them all the time. It's not going to be that comfortable. But if you're comfortable doing the problems, you could just go through and overcome that.
Right.
Okay, that brings us, I think, to probably the last topic in this chapter, which is the last topic for the exam, which will be a week from today, right? That will be Tuesday, and yes, that's fine. I can address that.
Yeah, principle.
So this deals with Le Chatelier's principle. And Le Chatelier's principle, I think I brought this up in the past, but this is simply, I have a balanced chemical equation that's in an equilibrium. If I make an adjustment to one side of that equilibrium, it will then readjust itself to form a new equilibrium based on Le Chatelier's principle. And there are several different things that can cause that change.
This
Okay.
Thursday.
So I apply a stress to a system, to an equilibrium system, and the system will respond to relieve that stress and then create a new modified equilibrium. That's all that's saying. Okay.
The shot, yeah.
The Chatelain's principle. So what does that tell you? Would that apply here? I want to make sure this is really, seems like a simple concept, but I want to make sure it's clear. Would that apply here? No, why not? It's not an equilibrium,
Right.
right? So if this was an equilibrium, then if I apply a stress here, which way will it shift?
Right.
Don't get confused by that. Depends on what stress I apply,
Okay.
right? I could apply a stress that forces it either that way or back this way. Same with here, here, and here. So if I increase the concentration of this, I'm applying a stress here, I'm forcing it this way. If I pull out some of this, I'm now bringing it back, right? Just to put that in context.
Right.
So I could add some or take some away. I could add a temperature or take it away. I could increase, if these are gases, the moles, and therefore the pressure, and that would adjust it, if they're not equal moles on both sides. Question? Steve? So there are a few different things that I could apply as stresses that I'm going to first discuss, and then we'll discuss which way it would shift a potential equilibrium and how to look at that relative to the balanced chemical equation. Okay, and that's what Le Chatelier's principle is. And I think you probably have already done something related to this in laboratory. So this should make sense. Okay. So different types of stresses. We just talked about concentrations of either reactants or products. Pressure, mentioned that, and temperature. Okay. So I have A plus B in an equilibrium with C plus D. If I add a stress to B, where I increase B, I shift the equilibrium to the right. And I now favor the products as a result of that. My new equilibrium, I'm just going to say I just put the prime, A prime plus B prime gives me C prime plus D prime. It's a new equilibrium. What do I mean by new equilibrium? Let's make sure that what I'm saying makes sense. K is different,
From the original.
and so are the what? Concentrations. I've adjusted the concentrations of the reactants and products. That's the new equilibrium in this case. Okay. So how did I do that? By adding some B here. What happens to C? Right? Increase C or decrease C? Increase.
Increase.
What about D?
Increase as well.
What about B?
Decrease. Oh, wait.
You increase in which one? You increase in
Let's
B?
get back to that. What about A?
Decrease.
Decrease. So now what about B again? I started with a certain amount of B, I added more B.
Oh, increase
Did
again.
all of that B get used up here? Probably not. It just went to some, so I lost some of the added B, but I still have some of the added B, so it overall went up most likely.
Right.
Okay. So this went down, this goes up a little bit, these go up also.
Right.
Because these are obvious that they go up because you've shifted it that direction.
What if like A is your limiting reactant and you just keep adding B? Is it?
Well, you'll still shift the equilibrium, but it may not go faster. That would deal with the kinetics of it if it was the limiting. Because you still have a certain amount with this that created this after, regardless of the amount of time it took, right? Well, limiting in the context that I think you're taking it, you could think of limiting as if this was just one direction. Well, then it won't matter, of course, right? Because if this is limiting and this is only one direction, then you've already used up all this, then it doesn't matter how much more of this I put in. But there's no equilibrium established either, right? So that would be under the percent yield, and when we went through the stoichiometry and all that kind of stuff, I think if you're referencing that, we didn't have equilibriums then, right? That's the difference, I think, between what you're thinking and what you're seeing here. Okay. Okay, so let's take a quick look here, the new equilibrium. C prime is greater than the original C, D prime has more than the original D, A has less, and then of course this one now, B prime is more than the original B, but not as much as the B star, which is the amount I put in with whatever I had at equilibrium. Right, so this is where I had this, I added some, I now have this, but now I'm gonna lose a little bit to get this, which is still gonna be more than this, my original amount. And that's the same kind of thing we talked about. Okay, so that's the establishment of the new equilibrium. So, adding reagent. Okay, so this is just going to be some real general stuff. Adding reagent generally shifts the direction in the opposite way, the opposite side of the equilibrium side. Right? Taking some away is going to shift it towards it. That's all these things say. Well, by the way, this is kind of an interesting point I should point out here. So when I add a reactant or a product or take away a reactant or product, at that moment, if I solve for the constant, what am I solving for there? QC.
Yes.
It's not equilibrium anymore, which is also called the reaction quotient, right? That's what we called it. So I'm actually solving for QC if I were to start right at that moment. From that, it would probably tell me which direction it would go if I couldn't figure that out just by looking at it.
Okay.
So if all these things didn't make any sense to you, just by looking at it, so if it did make sense to add more here, that I'm going to shift it this way, I could just put it all into the constant, find my reaction quotient, or my QC, and see where that is in comparison to the Kc if I knew the Kc. And if it was less than the Kc, then I know it's moving that direction, this way, right? Just to put that in context. So that's why it has the QC is less than Kc here and QC is more than Kc there. Okay. Removing reagent, so if I take this away, it's going to shift it towards it. If I take this away, it's going to shift it towards it. That's all that's saying. Just another group of fancy ways to say things that very simple meanings. Is that okay? Everybody comfortable with that? Especially after doing the labs, presumably? Okay. All right, let's do some quick examples. Initial concentration is given here, here, here. I'm going to have a change. It's given here. And then I'm going to have the equilibrium concentrations. So now I'm going to do something to either one of these reactants or this product. I'm going to add the stress here. I'm going to increase this reactant. What's going to happen here? This is going to increase. What's going to happen here? This is going to decrease. And since I now have 0.41, I'm going to have something greater than 0.21 after it reestablishes its new equilibrium.